In the last video, we had a three-dimensional surface where the height z was a function of x and y, and it gave us surface in three-dimensional space. Now let's try to get our heads around what the gradient of a function of three variables looks like. So the easiest one for me to imagine is a scalar field. So what's a scalar field? Well, one that I find fairly intuitive is temperature in a three-dimensional room. So let's say the temperature in a room is a function of where I am in the room. So let's say it's a function of my x, y, and z coordinates. And I don't know, I have never actually modeled temperature, but let's say I have a 20 Kelvin. Actually, let me make it so that our vector field works out right. Let's say we have a 10 Kelvin heat source in the center of our room. And so I can imagine as you go further and further away from that heat source, it's going to get colder and colder. So let's say that the temperature function, and let's say that center of the room is at the coordinates x, y, and z is equal to 0. So let's say our temperature function, I'm just making this up, I don't know if this is an accurate model of temperature, it's equal to 20, I keep saying 20, but let's say it's 10. Let's say it's equal to 10 times e to the minus r squared. Now why did I say r? I said it's a function of x, y, and z. Well, I'm just saying that it exponentially decays as you get further and further away from that source, kind of radially further and further away from that source. So what's a radial distance away? And this actually isn't that relevant to learning gradients, but let's get a little intuition about what that actual temperature function, how it actually changes as you go through the room. So the radius away from the center, that's just going to be the radius as r squared is just x squared plus y squared plus z squared. That's just the Pythagorean theorem in three dimensions. So let's write our temperature function. So let's write temperature as a function of x, y, and z is equal to 10 e to the minus x squared plus y squared plus z squared. Which is exactly what I wrote up here. I just, instead of writing x squared plus y squared z squared, I wrote r squared, just to kind of give you the intuition that this expression is just saying the square of the distance as we get away from the center of our room, or from the coordinate 0, 0, 0. But that's not what we're learning here. But I want you to understand, at least conceptualize this. It's hard to draw a scalar field. All a scalar field means is that in any point in this space, and in this case we're dealing with three-dimensional space, at any point in that space we can associate a value. And that makes sense. If you were to take a thermometer and measure any point in space in the room that you're in right now, you would get a temperature. You wouldn't get a temperature and a direction, so it's not a vector field. You would just get a temperature, and that's why it's called a scalar field. Associated with every coordinate is just a temperature. So how would we view the gradient of this function? Well, the gradient of this function is going to tell us in which direction, and actually the gradient of this function is going to generate a vector field, because it's going to tell us in which direction do we have the largest increase in temperature, and also the magnitude of those vectors in that vector field will tell us how large of an increase in temperature we are looking at. Or you can kind of view it as almost a three-dimensional slope. Hope that doesn't confuse you. So let's compute the gradient, and then I'll show you a diagram that might make things a little bit more intuitive. Let me erase this thing down here. And I'm going to switch from this blue color because it's a little nauseating. So the gradient of t is going to be equal to the partial derivative of t with respect to x times the unit vector in the x direction plus the partial derivative of the temperature function with respect to y times the unit vector in the y direction plus the partial derivative of the temperature function with respect to z times the unit vector in the z direction. And now we just plug and chug and figure out the partial derivatives. So the gradient of t is equal to Now you might be daunted. Oh, I have an e to this, 3-variable function. How do I take the partial derivative? Remember, if you're taking the partial derivative with respect to x, you just pretend like the y's and the z's are constants. So let's do that. So the derivative, let's take the derivative of the inside function. That's the way I have it. So minus x squared plus y squared plus z squared with respect to x. So you could distribute this minus if you like. So it'd be minus x squared minus y squared minus z squared. So the derivative of that with respect to x is just going to be, these are just constants, so they have, the derivative with respect to x is just 0. So the derivative is minus 2x, right? Minus 2x is the derivative of minus x squared. Minus 2x times the derivative of the outside. Well, what's the derivative of e to the x? The derivative of e to the x is e to the x. That's why e is such an amazing number. So and this 10 here, this is just a constant that, when you take the derivative of a constant times something, it's just the constant carries over. So the derivative of the outside function, or the outside expression, the way I imagine it, is equal to 10 e to the minus x squared plus y squared plus z squared. And then all of that times the unit vector in the I direction, right? And now we can do the same thing for the y direction. So plus, what's the partial derivative of this with respect to y? Well, it's going to look very similar. The partial derivative of this inner function with respect to y, it's minus y squared, so it's minus 2y, and then the derivative of the whole thing is just itself again. So times 10e to the minus x squared plus y squared plus z squared. And then all of that times the unit vector in the y direction times j. And then finally, the partial derivative of this of the temperature function with respect to z. And that's just minus 2z times 10e to the minus x squared plus y squared plus z squared. This is just the chain rule, and I'm treating the other two variables that I'm not taking the partial derivative with respect to as constants. And then all of that times the unit vector in the k direction. And we could simplify this a little bit. You could have, minus 2x times 10, that's minus 20x. Let me write it up here. So the gradient of the temperature function is equal to minus 20 e to the minus x squared plus y squared, you probably can't read this, plus z squared times I minus 20, this is minus 20x minus 20y. Actually, I'm not going to go into that because I realize I'm running out of time. I think you can simplify this algebraically. But anyway, the more important thing is, I always find with gradients, it's easy to calculate them, but the intuition, oh sorry, this is also included, this is a k right here. The harder part is the intuition. So let's get an intuition of what this gradient function will actually look like. So what would happen if you wanted to know the gradient at any point in space? You would substitute an x, y, and z in here. So the gradient function is actually a function of, you could write it as, the gradient function is a function of x, y, and z. But it's no longer, remember, t, to the temperature at any point, was a scalar field. At any point in 3 dimensions, it just gave you a number. Now when you have the gradient at any point in 3 dimensions, it gives you a vector, right? Because it has I, j, and k components, where the magnitude are the partial derivatives, and then the direction is given by I, j, and k. So we've gone from having a scalar field to a vector field. And let's see what it looks like. Let me make it bigger so we can explore it a little bit. I think that's pretty good. So this is the vector field. This is actually the gradient of the function that we just solved for. And as you can see, at any point, and when this computer, this graphing program that did it, it just picked different points and it calculated the gradients at that point, and then it graphed them as vectors. So the length of the vectors are just the magnitudes of the x, y, and z components, and then you add them together like you would add any vectors. And then the direction is given by the relative weighting of the I, j, and k components. And as you can see, the intuition is pretty Interesting. As you get closer and closer to our heat source, the rate at which the temperature increases. Right? The vectors, as you get closer, get bigger and bigger. And let me zoom in. Let's actually fly in to the vector field. So we're now within the vector field, and you can see as we get closer and closer to the center of our heat source, the vectors, the rate at which the temperature increases, gets bigger and bigger and bigger. Anyway, I hope I didn't confuse you. When I first learned gradients, I think the computation is relatively straightforward. It's just partial derivatives. But the intuition is always the interesting thing. And hopefully this temperature analogy, or not even analogy, this temperature model will make a little sense to you. But it applies to pretty much any scalar field. Anyway, I'll see you in the next video.